Alright, so today we're going to get into work and energy. Of course, conceptual, yeah, dynamic, so we won't be heavy on the calculus part. Our chapter objective, so we'll get into work energy, and of course we will relate that to your force, velocity, and displacement. Then we'll get into power and efficiency, yeah. Then we'll touch a little bit about your conservative forces and your conservation of energy. First, you have to know that work can only be done by force, right, on a particle if that particle moves from one position to another. If that particle, right, didn't move, even if you had a force on it, then you wouldn't have any work, yeah. So the particle got to move from one location or one position to another for that force to produce work, yeah. So work done by the force, we can use this formula. So your du, that's work, okay. This is just showing you the change in work because there was no work in this example, and then the work has been done because the particle has moved from this position to the final position, yeah, and it moves about this displacement, yeah, dr, times, of course, this force is going to give you the magnitude and also the direction of that work, yeah. So plus and minus, your direction matters, yeah. In real life, it's not this simple. You're gonna have a breakdown of your force, meaning like you wouldn't have always zero, right, degree angle. You're gonna have some form of angle when the particle move, it can be like that. So you always have some direction, yeah, or angle of direction, and you're gonna see several times, yeah, f times, and then you have your my c is bad, so cosine, right, cos, theta, yeah. This is just showing you the angle, right, the angle of movement. If you have like a force applied to a particle, let's just imagine there's a particle right here, yeah, and you're gonna have a little angle right there, yes. So in real situation, you will always have a cosine theta factor with your force, okay, when it takes a displacement, yeah. The displacement is going to be, of course, in this case, from here to here, yeah. We couldn't be able to say that the force that you apply to the particle is always move in a linear, right, linear direction. So it might just go off like that way, like your billiard, yeah. So you play billiards and your ball is gonna go different directions, and we can, of course, calculate, yeah, by using the cosine theta like that. Of course, for your course, in this class, we will deal with the linear, yeah, movement or direction, where your angle is always on zero, yeah, or 180 degree to that side negative. All right. Then we got to know the SI unit, yes. For work is Joule, right? J, and your symbol is U, of course. We use the U for work. And your formula is this, yeah, force times displacement. And don't forget to relate your displacement to your initial, yeah, and your final. So final minus initial is going to give you the displacement. Joule is your work unit in SI system. In British, we use a foot pound, yeah. Joule is nothing like if you have like a 1 Newton force, yeah, mass is in a force, because remember your F is equal to mass time acceleration. So your particle is in here, yeah. So when you have like a force on a particle, then the particle is going to take displacement of 1 meter, yeah. So that's about 3 feet and about 3.37 inches, I think, yeah, in foot-pound system. So about 3 feet displacement is going to happen if you apply 1 Newton force, yeah, and that is called work done, and the unit is joule. Okay, so 1 joule of work has been done by 1 Newton, if the particle would move 1 meter, yeah, from initial position to the final position. Make sure you study this. The rest of the 14.1 is just for reading, for your knowledge, because they will get into directional, yeah, work. So we won't be getting into it. Okay, just go with the mostly linear work, yeah, linear directions. Then we'll get into kinetic energy. So when you have a particle and that particle, right, move from one position to another, and we want to know with what kind of energy, yeah, this particle moves, and that's again 1/2 your momentum mv times your velocity, yeah, magnitude of your velocity is going to give you the amount of work related to the force, yeah, this particle has been subjected to, and we also call that movement, yeah, kinetic, yeah. The movement is done with the kinetic energy, yeah. So work's been done by a force. This amount of displacement take place. So what is the energy this particle, right, use to go from this position to that position? And we call that amount of energy kinetic energy. Yeah, the energy of a motion. Okay, so when you think about the kinetic energy, it's pretty much positive, because we are squaring the velocity, and this is your vector. Your mass is just mass, so it's a scalar, yeah. So when you multiply the scalar with a vector that's been squared, doesn't matter minus or plus, it's going to give you always positive. So your kinetic energy is also positive, yeah. So that's what this direction, it is always positive, it's talking about, yeah. Also pay attention to what you're looking at. Again, the energy, yeah, used in this situation for a particle to move from this location to the next, doesn't matter what forces, of course, and that particle moves with a velocity and with the kinetic energy of this amount. Okay. Alright, then we'll get into work in energy. So this equation is telling you the sum of your work, because you have like a two different, velocity that this particle is moving, yeah, and one point is moving with the velocity 1. At one point, the particle is going to move with velocity 2, yeah. So real life situation, we have like a different kinds of velocity that a particle use as it, yeah, move from one place to another. Doesn't matter that's a car or a ball that you're playing with, or basketball, yeah, football, think about it, everything. So anyway, so if you want to calculate the work, yeah, the sum of work, then you'll have to use this kind of formula where you will, yeah, minus the first kinetic energy out of the second kinetic energy. Okay, so this is kinetic energy of the particle using one velocity, and this one is a kinetic energy of the same particle using the second, yeah, velocity. So when you minus that, you're going to get the sum of the work, yeah. So that's what's showing here. That's the sum of the work. One going on two, yeah, particle moving with your final velocity. We can be able to quickly calculate the work, yeah, the sum of work, if you have a variable velocity. Yeah, your initial and your final velocity. This is just an abbreviation. Yeah, that's your kinetic energy with velocity 2, and this is your kinetic energy with velocity 1. So it's easier for you to be able to write the equation or read it. Yeah? And of course, we can move, since this is a minus, yeah, we can move this to that side. So we have all positive here. We can also find the t1, which is your velocity 1. If I ask you, go ahead and find what's the initial velocity, then you will want to use this equation by moving this, see this, the sum of work to that side. So that's your algebra and your mathematical expression. So anyway, we can write in many different ways. Yeah, we can write with the sum of the work, or we can write with kinetic energy with velocity 2, yeah, which is your final velocity, and then kinetic energy with velocity 1, which is your initial velocity. Yeah, and if you plug this in to here, you could be able to calculate v if you were given mass, right? So calculation wise is still non-calculus based, so you should be able to sorry, my software making sound. You should be able to write that. Yeah. Okay, study this one too. Don't forget that energy can be transferred. Yeah. So one motion, a particle is moving with a motion, and you got the energy if that particle in that motion is going to hit something on the way. So here I was just talking about, oh, there's a car, right? Oncoming car. It's going to strike these trash barrels right here, yeah? And the car's kinetic energy can be transferred to the trash, right? Cans right there. That's because when the car hits here, these barrels are going to definitely move from initial. There's no movement, see? They're just like sitting there, right? When something hit, the energy that this car, right, going, your kinetic energy. So some of the kinetic energy from that car will be transferred to the trash barrels here on the road, on the side of the road. Okay, so yeah, energy is transferable. Yeah, so when something touched another thing and something was in motion, another thing wasn't in motion, but when they collide each other, there goes the energy transfer automatically. Yeah, to the particle that wasn't moving initially. Yes. So when we calculate, right, to absorb the energy that can be transferred from oncoming car, right, to the side, with whatever a car accident that could happen to the car, you can calculate, right, by using the transfer energy into the crush cushion. Yes, so the crush cushion on the side of the road will definitely absorb the car's kinetic energy if the car is going to come off of the road and hit it. Yes, so that way you can alleviate the accident. Yeah, because you are stopping the transferable kinetic energy from that motion. Yeah, because every time you have a particle in motion, it is moving with an energy. Yeah, we call the energy of the movement kinetic energy. Yeah, and of course you can also stop that movement by developing crash cushion like that on the side of the road. Yeah, so that way the energy won't go off and transfer to other, yeah, unnecessary objects or stuff on the way. Yes, kind of like accident prevention. 14.3, we're gonna do only reading, so I can show you 14.3 here in your textbook is going to be this, yeah, principle of working energy for a system of particle, because we'll have to break it down into many different, yeah, direction in your coordinate system, so we won't be covering that for you. But if you have time, it's very interesting, by the way, and make sure you read it. Okay. Then we'll get into a little bit about power. So for power, oh, did I cover the unit for kinetic energy? One moment. So for unit of kinetic energy, we'll just go with the work unit, yeah, because it's the same thing. Your work is equal to the right differences in the kinetic energy when they are moving with different velocity in the same situation. Yes. So we'll use the same as your work unit, which is your joule and your foot-pound. Yeah. So their unit is the same, and that's because they're interchangeable. Okay. I forgot to tell you that, so come back here. So the work and your energy units are the same, joule or foot-pound, because they're interchangeable, and this equation proves that. Yeah. So let's go back to our power. So 14.4 is your power. When we talk about power, you've got to know this time, yeah, we're dealing with the magnitude of the force times the velocity, yeah. Now I'm gonna go back to your kinetic energy. Here we're dealing with the magnitude, yeah, of the momentum and the velocity, yeah. mv is your momentum and the velocity. And when we get to power, we're dealing with the force ma times the velocity. Okay, so a little bit funny, yeah, in your mind. I try to don't just get the equation. Okay, try to get how little their magnitudes are different. Yeah, we're just looking in many different ways: the force and the velocity, momentum and the velocity is your energy, force and the velocity. Yeah, is the power of that movement or motion. Yeah, so the term power, it's going to give you it's kind of like choosing the type of your motor or machine if you're thinking common sense, yeah, which is required to do a certain amount of work in a given time. So this is a common way of defining power, yeah, instead of going into mathematical expression like this. So you're like, oh, I have a motor and I have a machine, and you're very interested in how much of the power. So if you talk about the car, right, engine, we're talking about how much power this car has. Oh, Ford has more power than Toyota and things like that. Yeah. So you're dealing with, okay, how much force and velocity that this car can be able to provide me. You know, how much is this car power, and we're talking about that. Okay. So power is something to do with actually your work, okay, in a given amount of time. So we'll go to this equation. See, so this is your work, and again we're rating the power as the work done in this, all right, time interval. All right, how much work is done in this time interval is the power of that machine or object or something, particle, yeah, because it can do that much of work in this time. Okay, so that's a simple way of defining power. So the work done in a particular time interval is your work. Your power is the force time the velocity, yeah, on a particle. A particle can be anything, yeah. So that's also power, yeah. So average, again, just dealing with your change in work divided by a change in, yeah, time. So that's a delta U divided by delta T is going to give you your average, yeah. Average this machine, you know, like, oh, has this amount of power, yeah, it can do that much of work in that amount of time, yeah. Of course, it can do averagely if you think about the machine average, okay, power. You can calculate by using this equation, okay, unit. We usually use watt for power, yeah. You can see all kinds of electronic devices as power, yeah. We always check how much watt, right, and how much watt my house electric system can be able to provide. Yeah. Devices, your appliances, your refrigerator, your dishwasher, your oven. Oh my gosh, right? And they always have a little sticker in the back, and make sure you check it, and you're gonna see the watt. Yeah. Your portable generator, right? We always check, well, how much power this generator can be able to provide me. So 3,500 watt, right? This guy can do a 7,500 watt. Depends on the fuel type, right? Gas, and you have electricity, of course. So like electricity have a little bit of a lower power than the gas, right? For generator, portable generator. So pay attention when you go to Lowe's or Home Depot or local, local store, and you can always check out the power of these devices and machines. Yeah. And 1 watt is nothing but your joule. Yeah. This is because your power is your work done divided by your time. So we have work unit joule divided by the time unit s. Yeah, second. Joule, we know that that's your force, which is your Newton. Yes. And then of course velocity is meter per second. Okay. Joule is your Newton and meter for work. So because work is, you can also define it with the force times your displacement. Yeah. So this is your force and displacement divided by your time, and that's your second. Okay, well, my dog is walking in the back over there, so I apologize. So anyway, so horsepower is 1 HP. Yeah, horsepower equal to 550 feet times pound. Yeah, per second. This is just a force, by the way. So 1 horsepower is you can go about 550 feet. Yeah, times a pound. So that's a magnitude of that in 1 second. Yeah, so that's a pretty huge power. Of course, your giant machine, right, in a factory or manufacturing plant, you're gonna see the superpower machines like that. Yeah, this is just a 1 horsepower, by the way, and you can have like 550 feet times pound over a second. Yeah, that's very powerful. For conversion between the two systems of unit, so your watt and then your horsepower. Yeah, so that's your SI, and this is your British system, and we can use this conversion. This is 1 horsepower is equivalent to 746 watt. Yeah, so make sure you use this if I ask you to convert a unit. Okay. Alright, so that's all for your power for conceptual dynamic. So here, when you think about the power, you can relate that to your work, and then your force, of course, and your acceleration. So you understand that the power is for, in this example, your train. So you gotta overcome the friction, on your the train track, and also you gotta carry the weight of that train, and you have to have that amount of power in order for it to move, and take a distance, of course. So trains go from one town to another, and you can imagine we use fuel, right, to generate energy, because your energy with the amount of work you can do can be able to move, right, this object to one location to another. So you'll have mv square, right? So that's your energy, and your power again is your work, right, divided by your time interval. And in your work, you can relate in your mind to your force. Yes, your force, you can relate that to mass and your acceleration. And do I have to go back and show you again? Right, so here this joule is your work. And of course it's taken on, this one is your meter, right? So your distance, and then that's your force and that amount of time. your power again is the change in your work, and you are looking at, right, in a time interval. Okay, so how everything is so related to each other. So yes, and then you can be able to understand your work and your energy, yeah, because your work and your kinetic energy is also interchangeable. So pay attention. It's all about movement, moving an object to one place to another. You need a force, yeah. You need to generate energy. Use the energy to move, because energy is ability to do the work. And if you have a work done by the force, then you bring your time factor into it. Again, time factor is nothing but we are studying, right? An event, which is in this case is just a motion, yeah, from one reference point to another, yeah. So you have like a little time interval from the first reference point, time t1, all the way to t2. So you have like a delta t, which is your time interval, and we study the event during that time, and you get, oh, okay, we're moving this right amount of mass with that amount of velocity, creating this amount of acceleration, and that's our force, and taking that amount of distance, and you get your work. And when you study the work over the time interval, in that same time interval, then you get the power of that. Okay, in this case, the train course. Okay. All right, my dog is something's going on in the back. Let me check, and I'll be back. Okay, she is fine. All right, efficiency with this little C epsilon kind of sign right there. Efficiency is we're just looking at the power output, right, of a machine or device, and over, oh, how much do I, right, input the power, how much come out from that machine, and that fraction is called efficiency, yeah. Oh, I put this and I'm getting this much of output. My input power is this much, but my output power is that much. And when you look at it that way, we get efficiency. Okay, so if we have to define formally, then your mechanical efficiency of a machine, yeah, it's just a ratio, yeah. It's telling you the output of a useful power. This is a useful power output produced by that machine, yeah. So this ratio to the amount of power supplied to the same machine. Okay, so output power to the input power. So this ratio is called the efficiency. So your output is always be less than the input power. It's because the efficiency is always going to be less than -1. Yeah. Why? It's because your input is always greater than the output. Yeah. So in mathematics expression, so if you have like your denominator and your numerator, yeah. So pi is your denominator and this is your numerator in ratio. So the denominator, one denominator is big, then your ratio is small, yeah. So the efficiency is going to be always a small number, yeah, less than 1. We can also express the same efficiency, yeah, ratio in terms of energy. So in the first, we defined it with the power. In the second, they're all related anyway, power to work and work to energy, yeah. So you have energy output divided by energy input, which is your kinetic energy, yeah, output, kinetic energy input, and you're going to get your efficiency. Okay, so here formally, if energy supplied to the machine, which is this guy, occurs during the same time interval, because we are studying in a time interval always anyway, so it is drawn, then the efficiency may be expressed in this, yeah, energy term, in terms of the energy. So you got two ratio, yeah. The very first one using the power, and the second one using the kinetic energy. Procedure for analysis, just read it through because we're not covering all of the problems anyway. We're doing only conceptual selected problems. Yeah. So this is just for you to read through. It's just reviewing your force, right? Sum of force is your mass and acceleration, and then you have your power. Yeah. So this is your power in terms of your force. Yeah, and your velocity. And if we want to study the force in direction, different direction, then we consider the theta, yeah, of for the displacement to take place, and also the direction. Yeah. So when we deal with the coordinate system, of course, you have your cosine theta with your force, but don't worry about that part. We just cut it out in this first simple equation. Yeah. Then we come to our average. Yeah, power is your work, right? Change in work and your change in time, right? That ratio. Oh, we take a look at the change in work done over the change in time is your average power of a machine, okay, or device. Okay, then we'll get into conservative forces, and of course your potential energy. We study the energy of a moving, right, particle, and we also have to get into energy of the static, yeah, or staying particle, or particle taking a place in a space, yeah, because you always need you always need an energy to keep yourself at a location in the space, even if you're moving or not. Okay, so if you're moving kinetic, and if you're not moving taking a place in a space, then you're balancing yourself at that spot with your potential energy. Okay, conservative force, so we're looking at the force and the work done by that force, right? And we don't care about the path, right? Independent of the path, and it depends only on the force's initial and final position on the path. Yeah, and we call that the conservative force. So when you take a look at it, your force, right, independent of the path, and your initial, and then your final, okay, position, doesn't matter what your path is, right? Then we have a, let's say, just hypothetical force right there. Going from here, yeah, to there. Doesn't matter how it goes. You're going that way, you're going this way, you're going this way. We call this type of force in the study conservative force. Okay, it's just a change in the initial position. This is your initial position, and then I'm just gonna call it SI, and then this is your final position, SF. Okay, it's just trying to say the force is conserved if we don't count about how the particle, right, goes, whether taking a path A or B or C is going to change from one place to another, like your displacement. Doesn't matter what your distance traveled, the path is, yeah, like that. Your force is going to be conserved, yeah, conservative force, the same force. Then we will dive into energy, and I tell you so many times that energy is ability to do the work. You have energy if you can be able to do some work. So here, physics and in mechanics, energy is defined as the capacity to do the work. Okay, capacity is the same as ability. Yeah, your ability or a particle's ability to do some work. Kinetic energy, again, is your work, right? It's done on a particle, and it's going to bring that particle from resting position to another position with a speed, of course. So your 1/2 m, right, and then v squared. Okay, potential energy is nothing but your energy, right, ability to do the work, but it's like it comes from your position of the particle, right, taking a place in the space. We usually say like that. So measure from a fixed datum, that's just a kind of like a reference, just take it like datum is a datum point, yeah, or a reference plane, and we call it potential energy. It's just very formal way of defining. It's just talking about the object that is at rest, right? It's taking a place in a space, and with what energy that particle or object, right, is taking that space, taking that place in the space with this potential energy. Yeah, you always need an energy to either stay in a position or doing a move. Yeah, doing a movement. So for you to sit down, we imagine you as a particle. For you to sit down in your seat, you need energy, and that energy is your potential energy coming out from your body, yeah, your chemical stored, of course, in your structure, because you are just a system of organs anyway, yeah, all kinds of stuff inside of your muscles and your bone and your organs, everything's right in there in your system, and they of course have internal energy, and you use that, yeah, your energy from within to sit somewhere or stand somewhere or move yourself from one place to another and do some stuff, yeah. So anyway, so potential energy and kinetic energy is what we use all the time. Particles also, some of the particles can move by themselves, equipped with their own energy, artificial, yeah. Some of them are not, and we have to help them, yeah, because energy again is transferable, yeah. So if your phone can walk by itself, so you have to go and pick it up, right, and then operate with your hands on it, so you can use the phone, your cell phone, right? If you just put it on a table or on a sofa where I'm sitting right now, then it just stay right there. So with what energy is it staying, you transfer some energy into it, right? And then you place it in that spot, which is the place in the space, which is right now in my example, the phone is on a sofa, right? So that's your phone potential energy is the height, yeah, from that place all the way down. Right now, our reference point, your datum, or yeah, is your center of the earth, right? So that's our measurement. The height is in there. Mass is your mass of your phone, yeah, and you have your acceleration due to gravity is always pulling all the objects, yeah, towards the center of the earth. That's why we are on the surface of the surface of the earth, right? Stuck on it. So anyways, your datum or reference plane is where you study, yeah, where is this object or particle, yeah, what positions, or I can draw that for you so you kind of get it. So if we measure from a point like center of the earth, if we measure from a plane, yeah, also real reference plane, and then you're going to see where your particle is. It's from here to here, that height, yeah, away from each other. And your particle has a little mass, of course it is a particle, so there's some mass on it. And then you always have your acceleration due to gravity, which is a little g. So that's your m, g, and h. If you multiply all of that, you're gonna get the amount of energy stored in that particle, which is your potential energy. Okay, taking that place in that space. Yeah. So magnitude is that amount, m, g, and h. Multiply them. Yeah. You need that amount of energy to stay in that position. So anyway, so the potential energy is a measure, yeah, of again amount of work, because you gotta do the work to take that place in the space. Without the work, you can never be placed in there, yeah, and or take that location. All about energy. You need energy to be anywhere. Anyway, so okay, so that's with your potential energy. It's a measure of the amount of work a conservative force is going to do. Doesn't matter how the path is. Yeah, conservative force. It's just a displacement from here to here. We don't care about how it goes. Yeah, you can take the particle that way and place it, or you can just take it straight up. Yeah, or you can go a different path and then put it. Anyway, it's just a conservative force. Anyway, it's going to do like when it moves from a given position, which is this is my datum point right now, which I am measuring, yeah, from this point to there. And this is your position point. That's your datum reference point. And this, all right, is a distance or your height. Yeah. So it moves from a datum point to a given position. Alright, so that's up with your potential energy. So you have all the energy, yeah, just a regular energy, ability to do the work. We have a two major energy type. One is the energy for movement, the kinetic energy. Your particle is moving with a velocity, yeah, and we got to it 1/2 mv squared in magnitude. Potential energy, your particle is at a position, some distance, yeah, away from a reference point or a plane. Yeah, doesn't matter how it goes, it's just going with a conservative force. So if that work is done, move from from the reference point to a position. All right, and so we call that potential energy, which is the mass of your particle, the distance move. We usually define it as height. Yeah, and your acceleration due to gravity, g. Okay. Of course, our reference is the center of your Earth in that situation. If we go by MGH, we can always go with a different reference point, yeah, in different situation or problem. But it is the same thing. You have a mass and you have a displacement, and you've got something, yeah, like acceleration due to gravity, which define its motion from one position to another. Anyway, so that will get into gravitational potential energy, which we have already defined, but we will write it in a different symbols, this time. So Vg is your gravitational potential energy, V and G defines your gravitation. You have your particle weight, which is your weight is the same as your F is equal to ma, so weight is your m and g. If you forget about it, I can write that down for you. So don't forget, your weight is like your force, and you have your little mass, okay, times, since we're dealing with the gravitation, we're dealing with the acceleration due to gravity. Okay, my equation is like that. So that's what we're talking about with this W right there. Yeah. So particles weight, and then your distance. Most of the book go with the H, but here we go with Y, and that's okay. And distance, you have a direction. Yeah. Your datum in this example, your datum reference datum is right here. Yes. And if you go up, that's a positive. You go down, that's a negative. Yeah. So distance below and the distance above this datum point. Yeah. Of course, you have your weight pulling. Your pull is your acceleration due to gravity. Your Earth, center of the Earth, pointing towards it. Pointing towards the center of the Earth. Yeah? And then your mass is the particle mass. Okay. So don't forget. Don't forget, you should be able to link in your brain, yeah? So make sure you study that. And here it's just showing you your gravitational potential energy right here below the datum, so minus work, and then Y above the datum, so plus work, and then Y. Your work is your m, and acceleration due to gravity. M is your mass of this, yes, little particle. Okay. Okay, see this crane and lifting this cargo up from this ship. So going up, 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 up. So your distance, yeah, going up, which is this guy, yeah, which is your Y. So distance above your datum, yeah. So we can take the datum point as a level with this ship. We can do that. Or we can also measure from the center of the Earth, yeah, doesn't really matter. So this can go up, to different distance. Yeah, if you go here, then you're gonna have your potential energy. Yeah, and if you go here, your potential energy is going to be different. Yeah, as you go up, so it gets positive. I just want to show that it will go up. Yeah, energy will go up in magnitude. And if you go down, if our so anyway, so if you look at this, yeah, I can do it again by drawing. Yes, if you draw this, you can be able to see, oh, this is my datum point. Everything that is below negative, that's a positive. So if you move this cargo, yeah, right here, you're gonna have a different potential energy than moving the cargo to right at that position. Okay, so make sure you all understand your potential energy. Okay, it's just a change in a different direction away from your datum point or datum plane. Okay, reference, yeah, reference point. We always measure from a reference, otherwise you can't be able to know, yeah, know how much of the distance you have moved or how much of the work you have done if you don't have a reference point to study. Alright, we will get into a little bit about the elastic potential energy. Yeah. So when you study a spring, yeah, elastic spring, usually it looks like this, right? I can draw it horizontally like that because this doesn't look very good, but you can also just assume that, yeah, it's the coils are the same. I don't draw nicely with this mouse. So potential energy, again, you can store in the spring, yeah, because when you stretch it, you will definitely have a distance, right? So if you pull it to that direction, let's say this is my reference, right? Point here, you will definitely go that amount of distance, right? So here, of course, they use a little s symbol. That's just a spring constant, yeah, amount that it can be constantly applied to the spring is this much k, and then your displacement, your distance that you can go from this datum, yeah, right here, or reference plane, from that to here, that distance you can pull. The plus is like going to that direction. Your measurement reference point from here, yeah, and if you go to that side, of course it's going to be negative. When you release it, it will just go bounce, yeah, like that. The same thing, you can make a datum right there and pull to this direction and make it like, oh, that's a positive. The distance is about this much, yeah, you can pull. And of course, the spring has a unstretched, right, position. It's your potential energy, elastic potential energy of that spring. When you stretch it, you have that potential energy change into kinetic energy, taking more distance, yeah, away from your unstretched position. Since you're dealing with a change in position, again, you're dealing with the potential energy, because the potential energy was studying, yeah, change in position from a reference point of a particle with a mass, yeah. And of course, when you change that position, the particle has moved, and when it moves with some acceleration, yeah. So you have your acceleration, mass, and the distance, and that's your potential energy. Okay. All right. Again, when you pay attention to the mathematical expression, you know that you're dealing with a square. That's constant. Yeah, in constant, since it is a constant, you always have a positive, right? A value. So the whole thing is positive. That's what it's talking about. It's always positive, yeah, in a deformed position, because the force of that spring has ability or capacity or potential, right? Doing the positive work on the particle. All right, so that's with your elastic potential energy. So if we need to sum it up and stretch, okay, your spring like this, you can compress it, yeah, this is compressed, you compress this much, yeah, and stretch, we can have a reference point from here too instead of there, yeah, and you can stretch it out ding, 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 to here. So now your stretch position distance is that much, okay. This is our original, thus your compressed distance, and this is your stretched, okay, distance. So we just elongated, we just go with a little e like that, okay. And of course you have a acceleration when you pull it, when you press it also you have a acceleration, okay. And you're dealing with a mass because the spring has a mass, which is we usually use a K, yeah, which is your spring constant. So instead of mass that we are familiar with, we usually write it, K, okay. So that K and your movement, yeah, movement with your force, right? Because you gotta either press it with a force or pull it with a force. So there goes your mass of the spring, and your acceleration will incorporate into that force, and that work done, okay, will be transferred to the ability of that spring to do this work. So we call that the energy, yeah, potential energy, because you have a spring constant and then you have a change in position. See, from again with from this datum point in this example, I was drawn in a different way. Here I draw this vertically instead of horizontally, yeah. This is your unstretched normal, yeah, compressed, elongated, and you have a different potential, yeah, energy, which is elastic potential energy, because the spring has elasticity, yeah. It's just a nature of a spring. Okay, so that's for your elastic potential energy different example. Now we are going to use a textbook diagram, yeah, so you can be able to see it better. So here you have your K, and then this is your and stretch position. Potential energy is completely zero, because we have an stretch position, original position S, which is zero, yeah, your reference point, because we are measuring the new distance from that point zero. Now we're going to stretch it, so you have your elongated distance. So we're gaining plus S, yeah, so that much of distance from your reference point zero, yeah, which is this datum point right there. So now we have a plus S, yeah, distance away from that reference point. So you have that amount of potential energy in it, okay. Well, then we're going to compress it to minus S. Again, your reference is right here at zero, so going to that direction is negative, going to this direction to the right is your positive, yeah. And so you get elastic potential energy, which is positive, yeah, 1 by 2 ks squared. Why this is still positive is because it doesn't matter positive or negative, we're squaring the s in our formula, yeah. So therefore your potential energy is always going to be positive for elastic, yeah, elastic potential energy. And I don't want you to confuse, okay. For here, pay attention, you have a distinct, yeah, positive and negative. It isn't always positive in gravitational potential energy, but for spring it is, okay. Elastic potential energy is always positive here, yeah. So pay attention to these little things So our formal mathematical expression is your elastic potential energy is equal to always positive 1 by 2, and then K constant, and then S squared. So pretty much looks like your kinetic energy, yeah? And your T is equal to 1 by 2 mv squared formula, yeah? Very much like that for elastic potential energy. It's just the mass is changed into spring constant, yeah? So then we define each symbol. So that's your elastic potential energy, and this one is your spring constant, and S is your distance from end stretch, of course, a position here, yeah, your reference position. So here we have a potential energy in the spring. Yeah, this is your spring right there. You also have some weight, and that's where your force is, yes, and transfer into your potential energy stored in this spring. Yeah, so this is a real life example for you to be able to see. So every time you remove, right, a layer, this is stack, so you have like a weight on it, so you can remove one layer after another. So as each stack is right being removed, you're gonna have the platform rise, right? So you can see the change in the distance here, yeah, from, let's say, just you have your reference point there. So every time you remove this, and that distance is gonna go up and up and up, yeah, depends on the weight of it. So lighter, the distance is going to be higher, yeah. So that way you can remove one after another, and the spring is going to go up and maintain the height, yeah. So you don't have to bend over. So your algo is going to be not that bad, yeah. I mean, like, you won't have a strain in your body. Okay, this is just a review. You have it at the end of your chapter, yeah. Just pay attention to your work of a force, yeah. Don't worry about your cosine stuff. I'm not going to ask you. We'll just use a simple conceptual, right, formula instead of mathematical calculus or one, yeah. So won't do the coordinates systems on your forces. And then of course then you get into your work, yeah. Then we get into kinetic energy in your spring, but we don't get into the spring force. You don't have to do that, just the kinetic energy. But then know that your kinetic energy can also, right, to be written in terms of spring, which is like, this is kind of like an mv squared, but for spring we use a spring constant k, and then your s square, okay. Of course you have like a different position, so you have 1 and 2. And your work and energy, they're interchangeable. So your work and then your kinetic energy, we talked about that. Your power and efficiency. Your efficiency is the ratio, your output and input of power or energy. And then your power is you're looking at the change in work over the change in time. Yeah. We can also get the magnitude of the power by applying the velocity with the force on that object. Yeah. Then we come to the conservation of energy, yeah, and we study two things: elastic potential and also gravitational potential energy. Yeah, that's a conservation of energy, because your force doesn't really depend on the path, yeah. It just depends on one point to another, yeah. Meaning like the force can do the work, yeah, independent of its path. Same thing here, and here is your potential energy, and that's your datum or reference plane going up and down, and you have a direction changes plus and minus, yeah, which is affecting the magnitude of your potential energy, yeah. That's your gravitational potential energy. And don't forget, your weight is your mass time acceleration due to gravity. Then for spring elastic, potential energy, we also go with the unstretched position as your datum point or datum plane, and we measure from that point, right, going stretch position or compressor position. But doesn't matter how your position change from your reference and stretch position, it will be cancelled out with s being squared in the mathematical formula, so you will always get a positive for your elastic potential energy. And that's what we're talking about. This mechanical energy, you are dealing with your kinetic energy, and then you're dealing with your gravitation or elastic potential energy. In here we're dealing with the conservative forces, and also the conservative energy, of course. Alright, so that's it for your chapter 14, okay? So make sure you do your review exercise, your quiz, and then your equation assignment online.